This video system is designed to introduce the apprentice machinist to the mechanical concepts of the vertical milling machine. This universal design is the most popular. It has been used by manufacturers around the world for many years. As we study it, you will come to understand its appeal. This design has found the right balance of versatility, accuracy, ease of use, and price for the general market. Since a variety of CNC milling machines are based on the standard milling machine's design, it is important to have an understanding of the principles involved. You will find that the geometric and mechanical principles are relevant to all machine tools, even when the construction is different. To get the most from this presentation, watch this video in a quiet place with your full attention. Next, run the machine with qualified supervision, practice what you have seen, and raise additional questions. Then watch this video again. Remember to take care of the equipment and make sure not to damage it. It was designed by machinists for machinists. Super strength and cheater bars are not needed. The ways are very flat and straight, with wear-resistant surfaces. They guide each axis and are assembled precisely 90 degrees or perpendicular with each other. Ways absorb vibration and the forces created by the cutting action. Keep them clear of abrasives and other objects to reduce wear and interference with movement. Remember that they require oil daily. The X and Y axes and the knee all have lead screws that push the components along the ways. Lead screws are wear items and also require oil daily. There is always slack as the lead screws are reversed, changing from push to pull. This is a constant concern. Slack is the table's ability to shift back and forth. In this illustration, the table is being fed from left to right, while the cutter's force is pushing the workpiece in the same direction. The result is that the cutter pushes the table to take up the slack on the right side. This is the proper method when making a cut for either the X or Y axis. The table's feed is pushing into the cutter's force. The digital readout system increases accuracy. They also provide great improvement and convenience by displaying spindle position anywhere within the workplane, and a zero location can be set at the push of a button. Another great advantage is reducing positioning concerns because of slack in the lead screws. This is accomplished by mounting a glass scale to the movable table, and an electric eye to a stationary component. The eye will record the slightest movement of the table, and the readout will display the amount and direction. The quill is the only axis that is not permanently aligned. It is normally parallel to the knee's travel, and perpendicular to the X and Y axes. When is it necessary to indicate the head and the vise? Assume we have a very precision part that is finished on the outside but requires a precision milled pocket in the center of the block. It is critical to hold this piece parallel with the x-axis, so the inside feature is cut parallel with the outside of the part. It is also important to consider how the head will affect the pocket. The z-axis alignment becomes more critical as the depth of the pocket increases. While the feature might be in tolerance at the top of the block where it is easily measured, it could be far out of tolerance at the bottom of the block. To accomplish this level of precision, we need to indicate the head and the vise. How do we ensure the spindle is perpendicular with the mill's X and Y axes? First, look at the angular scales. They should both be set to 0. Second, make sure the indicator is properly installed. The plane generated by rotating the spindle will always be perfectly perpendicular to the center line of the spindle bearings. Let's consider both pivot points before we begin. When bringing the head into perpendicularity with the x-axis, notice that the pivot point is in the center of the movement. If one side falls 10 thousandths, the other side will rise 10 thousandths. Bringing the head into alignment with the y-axis is quite a bit different because the pivot point is off-center. This causes the front and back readings of the indicator to rise and fall together, but in different amounts. Now, bring the indicator into contact with the table. Make sure it is set to 0 when it is directly under the pivot point. When you rotate the indicator to the right and left, notice that both readings are the same, but one reading is in the positive and the other is in the negative. Now crank the adjustment bolt and drive the needle to 0. This step will probably need to be repeated until the proper level of accuracy is achieved. Next, if we rely on the head's 0 in relation to the x-axis, the y-axis can simply be driven to match. This step will need to be repeated because when the head is raised for the y-axis, the x-axis reading will change slightly into the negative. The indicator will need to be reset to 0 in relation to the x-axis and then rotated to the y-axis for another adjustment. After all bolts are tight, make sure to recheck in case any movement occurred. The vise has an optional base with a pivot pin in the center. Like the head, it is important to understand the pivot point before we begin. When placing the vise on its base or the table, make sure that everything is free from chips and debris. Even a hair could cause problems. Since this pivot point is in the center, when one side of the vise is moving toward you, the other side is moving away the same amount. Let's consider the same concept, but we will use indicators on either side of the stationary jaw. Both indicators have the same reading, but one needle is on the left side of 0 and the other is on the right side. The object of indicating the vise is to make the vise run parallel with the x-axis, which is ultimately derived from the ways of the machine. Now, to accomplish the same goal without the optional base will be different, because the pivot point will change locations. We will need to use one of the bolts as an anchor and remove the other. This anchor bolt will need to be snug but not tight, allowing the vise to pivot a small amount. Viewing the new readings shows that this process will be more difficult to predict. What exactly are speeds and feeds? Speeds are the tool's revolutions per minute, or RPM. Feeds are the tool's linear or radial movement measured in inches per minute, or IPM. Let's look closer at figuring our RPM. What do we need to know in order to set the RPM? The diameter of the cutter, the material of the cutter, and the workpiece material. What is the average RPM range of a standard milling machine? In high gear, the maximum RPM is around 3,000, and in low gear, about 400. The spindle can rotate as slow as 75 RPMs in low gear, and in high gear, about 400. Let's say that our tool is a half-inch high-speed steel cutter cutting mild steel. This is the most common application in an educational environment. This works well at 78 surface feet per minute. It is worth remembering a shortcut formula for 78 surface feet per minute. To maintain that, a 1-inch cutter would have to run 300 RPMs. That makes 300 a key number to remember because 300 divided by the cutter diameter equals the RPM that results in 78 surface feet per minute. Therefore, 300 divided by a half-inch cutter gives us 600 revolutions per minute. Let's look a bit closer. If a 1-inch cutter rotates 1 revolution, a half-inch cutter would have to rotate 2 full rotations to cover the same distance, or surface feet. So after they have both traveled 78 surface feet in a minute, The half-inch cutter had to rotate 600 times to cover the same distance. Now that we have our speed, the proper method to set the machine to this RPM is to switch to high gear while the spindle is off, and then turn the spindle on. Make sure that the cutter is rotating in the proper direction to make a cut. And then adjust the speed dial to the suggested RPM. We have covered how the RPM represents the tool's rotations measured in minutes. Now let's consider the feed rate, which is how fast a table or workpiece moves into the cutter. This is normally calculated in inches per minute, or IPM. What do we need to know to calculate our feed rate? We need to know the tool's RPM, the tool's number of flutes, and the chip load, which is available on the tool manufacturer's website or charts. You will find that the chip load is proportionate to the diameter of the cutting tool. A 1/1000th chip load is conservative for our half-inch end mill. For our example, we are running at 600 RPMs with a 4-flute, half-inch diameter cutter cutting mild steel. Multiplying the chip load by the number of flutes or cutting edges gives us 4/1000. The chip load is the amount of material removed by one cutting edge. With a 4-flute end mill, every rotation makes 4 cuts. Since each flute cut 1/1000th of material every rotation, the tool must advance 4/1000 into the work each rotation. If the cutter is rotating 600 revolutions every minute and can safely travel 4/1000 every rotation, how far can the tool travel in a minute? Multiplying 600 RPMs by 4/1000 gives us 2.4 IPM. In this illustration, we have mild steel and aluminum being cut by high-speed steel and carbide. Our current application is on the far left. Notice the different cutting speeds. This is not attributed to the increase of chip load, but to the increased RPM. Aluminum is softer than mild steel, therefore easier to machine. Carbide is a harder material, therefore it can maintain a sharp cutting edge at higher temperatures. These materials allow the RPM to increase, so the feed rate will follow because it is based on the RPM. If the feed rate is too slow, the tool will rub, increasing friction and producing heat. This can ruin a cutter and work-harden alloy steels. When a cutting tool is engaged into a piece of material, the friction produces heat, which will eventually break down a cutting edge. To reduce heat, consider using coolant, and by setting your speeds and feeds correctly, you will increase tool life, the safety factor, and the quality of your work. Approved safety glasses are the most important item against flying chips, air blasts, and grinders. Keep in mind that rotating tools will grab clothing, hair, rags, or your finger. When cutting tools, gears, or fan belts are in motion and in contact, they will grab and pull in anything on one side and push away on the other side. Burrs are very dangerous, sharp edges, and the most common cause for cuts. All corners of the machine part will be sharp. but the edge where the cutting tool exited the workpiece will have the biggest and sharpest burr. The material will fold away, leaving a dangerous edge that needs to be removed. Consider an R8 taper on our application. It is designed with a straight section for a very close slip fit, a clearance section, and a tapered section at the bottom. A keyway is located in the spindle as a guide, while the collet is drawn tight into the matching taper by the drawbar. This is a locking taper. The collet must be drawn tightly to resist the cutting torque. R8 tapers are among the smallest and can be overloaded with large diameter tools and heavy cutting pressure. A flatter angle would not lock in the spindle. A slight taper would become too tight. Collet tool holders are designed to collapse onto a particular size tool shank. The collet and shank stack solid in the spindle. If the shank is over or undersized, the collet may be damaged and the tool will probably not be held tightly. After replacing the collet, never forget to remove the wrench from the drawbar. The manual milling machine may appear solid and massive, but it has been sectioned into many pieces and bolted back together. This increases the versatility and axis of movement, but it makes the machine much less solid and rigid. When a thin, brittle cutting edge is engaged into a piece of steel, you don't want vibration. The cutting edge can be broken away. This explains why rigidity is so important to tool life. The best way to improve rigidity is to shorten the loop of force as much as possible. Several changes in your setup will help, such as clamping the workpiece directly to the table, raising the knee and the quill, moving the ram and the saddle close to the column, and using short tools that are mounted in a collet. It also helps to lock all the travel locks. When taking heavy cuts, these techniques will make a big difference in tool life and vibration. Material removal rates will be dramatically increased.